Hello, we're Team ZetaCubed. This is our EAB Final Presentation for the spring-loaded dampening mechanism. I'm Alex Blakely. I'm the team manager in charge of budget and design.
I'm Austin Piper. I was doing the timeline, the design, some programming, and fluid mechanics.
And I'm Finley Butler, and I was also working on the design and the mechatronics analysis.
So to reintroduce our project, the problem we're trying to solve is that the servers at Intel, they had to be manually opened and closed, and you could save a lot of time and prevent possible damage by introducing some kind of dampening server self-opening hinge system. So that's what we're trying to do.
And some of the requirements for our server, the hinge has to overcome a moment, and that's the door opening. And we also want it to be able to take cyclical loading, and the prototype should be scalable and easily reproduced. That way we can introduce it to the market. And our design process, we got familiar with 3D printing, and we came to a consensus as it was cheap and was very automated. And it offered a lot of different materials that we were able to use. And so a lot of our research was done to find out more about 3D printing, and we looked to other sources to get feedback on different techniques and just self-taught ourselves using design for manufacturing and assembly to orient and optimize our assembly.
These are a few iterations of our design process. We've had to scale up and scale down to get the thickness right and see the correct orientation for printing. We had to increase our wall thickness overall by quite a bit because when it was printing initially on the far left, it was very thin and stringy. And we had to learn more about 3D printing and the size of nozzles and how that determines kind of our tolerances and how small of changes we can make in our design. This is a Cura file of our 3D print top hinge and bottom hinge. In the blue, it shows our tree supports that are designed to help support the 3D print as it's warm and the filament cools down and it doesn't sag or change shape from our 3D CAD files. For our materials, the biggest part is 3D printing. It's very cheap, and there's a variety of materials from nylon or PLA. It's super durable. PLA's biodegradable. And for the rest of our hinge, it's just a spring, and we have decided to use a stock spring from Lee Springs, and it's made of music wire.
So after we created one of our final prototypes, we decided to do some testing. One of the initial ones we wanted to do was, and the most important, was vibration testing. So we originally wanted to use an accelerometer. They're a little bit expensive. So we decided to use something called a geophone after doing research for alternatives for accelerometer type things. All a geophone is it's just, as you can see in the figure in the bottom left there, it's just springs that go over a permanent magnet. And so every time those springs are moved, it'll create, depending on how much movement there is in vibration, it'll create a voltage that we can measure. And so we performed a lab, and so far the lab was done without our hinge because we were having a little bit of trouble mounting the hinge so far. But as you can see from the next slide, so the goal for this one was, since it's going to be measured in voltage, we're going more for like how much in percentage wise, like magnitude is going to be taken down, not exactly the exact hertz are going to be damped. And so that's part of the reason why we did it. And so you can see on the figures to the left, that's basically how we did it. We mounted the geophone in several different locations, and then we read the voltmeter min and maxes, and then we put it on the door itself where we opened and closed it. And then inside the server itself. And so as soon as we can get our final prototype mounted, we'll be able to complete the second half of this experiment. And then one of the other ones we did as far as testing was we did a full finite element analysis. And so the first process we had to do was the pre-processing. And part of that was finding the governing equation. And so we decided to use Hooke's law because we were doing it mainly on the springs, the torsion springs. And so we basically created nodal equations after we divided it up into 3 different nodes. And then we created equations for each one of those nodes, and then we created a global matrix based on those. And those will be attached in supplementary in Excel spreadsheets on the supplementary notes if anybody wants to look at it.
And to compare with the Excel files, we're also conducting ANSYS simulations. We modeled inside ANSYS, inside the space claim modeler. We used the Lee spring specifications to model our spring, and we're gonna look into the deformation, stress, and strain of the spring.
For our 3D print filament, we want to determine the best percentage of infill and the best print structure and geometry. That we decided we were going to do a few different infill percentages with a few different printing pattern structures, and we created a tension test specimen CAD file and 3D printed it, and this is our tension tests starting to print, and on the left is showing our infills that we were wanting to do, where we go 30%, 50%, and 70%, and then the rectilinear, cubic, and honeycomb infill patterns. On the far right, it shows the result of that tensile test, and we are still working on those test specimens.
And like any long-term project, we've been faced with a lot of roadblocks. For all of us, this is our first experience with 3D printing. And so a lot of time has been spent troubleshooting and just learning about 3D printing techniques. The nylon filament that we also had access to has a lot of moisture that it absorbed because it was out in the open. And so needing to get a new roll of nylon filament that will increase the quality of our print. We also have a gap in our server door, and so looking to introduce a spacer into our hinge to cover that gap, and also the movement of the door while it's opening. And the tension test is also out of order, and so we're waiting on software updates from the materials testing lab. So once we get those tension test specimens printed, to be able to use that. And we're looking to use print in place, which allows us to print everything together and have motion in those parts. And right now those parts are fusing together, so we're just gonna have to keep printing with some trial and error. And this is our current prototype inside the server. And we're currently looking into the mounting points and the design of fasteners. We've picked up some fasteners that we just need to attach to the server door, and we can test with the hinge attached with those fasteners. And the biggest problem right now with the springs is they're way stronger than we initially designed, so we might have to either scale down or just reduce the number of springs for that moment arm.
And so this is the prototype in action. And so we basically tested it like this. It takes a lot of force. We haven't measured the force yet. We're gonna wait till we designed it so we can actually mount it in the server. And as you can see, we're pushing on it really hard, and it didn't break until we actually tried to break it later. And so as far as budget, we're extremely under budget, mainly because of the resources we've been able to use from school. So for example, a lot of the 3D printing, we haven't had to pay for filament at all. And so that was probably around $150 right there saved because we've used about 2 rolls. And we just bought another one of nylon. So that was a large amount of our budget taken out. The geophone itself would have been the most expensive singular piece at about $75. But that was our main method of testing we've been able to do so far due to downed equipment, like Finley said. Yeah, and so we have a remaining budget about $348.29, which is like massively under the $500 that we were given, but that's, like I said, mainly due to school resources.
This is our timeline, and this shows the first semester, and it shows the actual dates that we completed things, and when they were due. For the bolded dates are for our senior design class, and those are required, as well as the EAB requirements. And in the second semester, we have stayed on track. The biggest fallback, again, has been our printing. It's our first time 3D printing, and printing issues have been around the entire time. And so right now we're still on track to print our second prototype and begin testing that in the next week or so.
And so the last finishing steps we have to do is basically finishing our vibration testing. And so that'll be as soon as we can mount it inside the server, we should be able to finish that. Be really quick. And as soon as the tension and torsion machine is fixed in our materials lab, we'll be able to conduct that. And so that'll help us lock down exactly what we want to do as far as infill and pattern wise. We also want to make sure that we have a streamlined way to 3D print it so anybody can do it. And so that's where the printing in place will come in. We want, like Finley said, to make it so we can print off the entire thing in one piece, but it'll still be able to move. And then after that, we just want to be able to streamline it so the door will actually be able to open the way we want it to. And we look forward to hearing your feedback. Thank you very much.